Hello, everyone. This is the first time I've given a talk that has a soundtrack in the background, so we're going to have maths and jazz, apparently. And this is a surprising turnout for a really hard maths talk, like an abstract maths talk, right after a very absorbing keynote. I'm surprised that people are here and not off to go and write Rockstar, so I'm very flattered. So yeah, my name is Eli, and I am here today to talk to you about the maths that powers our encryption, how we keep our data safe when we're sending it over the web and things like that. I've been in tech for about 8-9 years now. I studied maths at university, which is where a lot of my love for this subject has sort of, I love this subject, and some of the things that I did, I studied at university. And yeah, I'm gonna talk to you about how asymmetric cryptography works, the actual maths behind it. I've got some worked examples, and why precisely quantum computing is going to change things and why quantum resilient cryptography is needed. So, agenda for today, I'm going to give a very brief history of cryptography up until the first asymmetric crypto systems. I'm going to talk about RSA encryption, take you through a worked example to show how it works, and then we'll talk a little bit about the actual sort of group theory, essentially. I'm going to teach you how elliptic curve cryptography works, also with some group theory involved. Unfortunately, we don't have doors here that I can lock so that you are forced to stay for this part. So you are free to leave, but I hope it will be interesting to you. This is the heaviest math section of the talk, and there is a worked example of the elliptic curve digital signing algorithm at the end of the talk, which I don't go through live, but if you want to come talk to me about it afterwards, please do. And then we're going to talk about quantum computing and Shor's algorithm and what that means for the world of cryptography. I see a worked example of how it breaks RSA encryption. And then finally wrap up with talking about what the world of cryptography is going to look like in the future, or what I hope it will look like in the future. So, a brief history of cryptography. People have wanted to send hidden messages to each other for basically as long as we've been talking to each other, especially since we started having things like armies and spies. So this is a very natural need that we have to try and send information to each other without somebody unwanted being able to obtain that information. And a very basic crypto system, something called a Caesar cipher, works like this, where you take letters of the alphabet and you just map them onto other letters of the alphabet. And you might do this by simply offsetting them by a certain number. So I would say NDC is great, and I use this mapping here, and I get something out at the other end. And if you don't know how I did that mapping, it might be hard to reverse it, right? What we're doing here is we're essentially translating letters of the alphabet into numbers, performing a mathematical operation on those numbers, translating them back. Now, this is a very easy cipher to break. This is a Caesar cipher. We are using adding 6 to our numbers every single time. You can break this very trivially with letter frequency analysis, right? This is very, very easy to break, very insecure. However, at one time, this was military-grade encryption because it was used by the Roman military. So, or at least apocryphally, it was. But we can extend this idea, and instead of adding the same number to each letter every single time, we can do something where we take each letter, we turn it into a number, we take another message text, something that's not known to outside people, and we turn that into numbers, and then we add both sets together, and add both sets together, take the modulo of 26, because that's how many characters we're playing with here, turn that back into some text, and this is an example of using a private key. This is actually what a lot of modern encryption uses, because if you use a large enough private key that is not known to an outside reader, this is very, very hard to break, because letter frequency analysis doesn't work on it. Of course, once the private key, if you had a private key that was very, very short, it becomes easier and easier to break. And the drawback of this is that in order to use this mechanism, you both need to know the string private key, right? You can't actually I can't send you what's on the bottom and have you understand it without knowing what I did to get there. So this is not asymmetric cryptography, this is symmetric cryptography, where both parties share knowledge. They have a symmetric amount of information, they have the same information. And so in order to communicate privately with somebody using this mechanism, you need to have already set up a shared secret. And this is hard to do. And this is why we have asymmetric cryptography, because of this requirement for symmetric cryptography. Once we have a shared secret, this is very, very fast to do and very, very secure. So the bulk of web traffic is actually encrypted with symmetric cryptography. But in order to get to a stage where we can even do that, we need something else to establish that shared key. And if you want to know more about this, you should look up how the TLS handshake works. So before I started, I should have probably asked some level-setting questions. Who here has a maths background? Okay, yeah. Who here doesn't know how the TLS handshake flow works? Okay, that's okay, only a couple. So yeah, go look that up if you want to know more about the interplay between symmetric cryptography and asymmetric cryptography. But the sort of the spark notes here is that in order to do secure web traffic, we need both, right? Or secure and performant web traffic, we need both. And this is where, yeah, we start to need asymmetric cryptography, which is what you can use in order to establish a shared secret, establishing a private line of communication. And the first asymmetric cryptography system is RSA. So has anyone here not heard of RSA? Cool, grand. So we've got, like, I think I saw a hand there. Brief facts for context. It was officially published in 1977, and it was groundbreaking at the time. And what RSA RSA stands for Rivest, Shamir, and Adelman, the three people who officially published it. Diffie and Hellman had published their key exchange mechanism in 1976, and it had inspired a whole wave of interest in the idea of asymmetric cryptography and the ability to communicate privately. Funnily enough, there was also a guy called Clifford Cox in the UK who had basically discovered it a few years before, and GCHQ had gone, well, that's cool, but we don't know how it would possibly ever be useful, so let's just shove it in a state secrets file somewhere. And it never saw the light of day from GCHQ, and it sort of came out afterwards that he'd actually also independently come up with this cryptography system. And what it does is it's security based on the fact that it's very hard to factor prime numbers or factor big numbers into their prime factors. All asymmetric cryptography is based on certain maths problems being very, very hard to solve with classical computers, essentially. And in the case of RSA, what we're talking about is the factoring problem, integer factorization being very, very hard. If I give you a big number and quickly tell me its prime factors, that is a computationally very expensive thing. And when we get to big enough numbers, it becomes computationally infeasible. To show you what I mean, we're going to do a worked example. We're going to use the very, very large and computationally difficult number of 323 so that it fits in our heads. So I'm going to do this to show you that the maths isn't witchcraft. This is something you can actually understand and fit in your head. This is a bad example for a bunch of reasons. Obviously, the number is very, very small, but also because 17 and 19 are very close together. In practice, if you're using RSA, although it's now becoming more and more obsolete, in practice, if you're using it, you want the prime numbers to be quite different in size. Right. So so first of all, modulo arithmetic, going to be very useful during this worked example. So we have this notation. A is equivalent to B mod n when they differ by some multiple of n. So what we need to know in order to set up this cryptography system, we need some secrets. We need some secrets to do with our big number. And the secret that we want to find out, that what we want to calculate that is going to help us do cryptography is something called lambda n. This is also called the Carmichael totient sometimes. And what this is we need to know if I have any number in the world and I raise it to the power of this number lambda n, then what that means is I have a remainder of 1 when you divide by n for any number, as long as that number shares no factors with n. And the only factors of n are 323 is 17 and 19. And we can work this out computationally if we know the factorization of our big number. And in this case, it's 144. And the reason we need to know the computation, we need to know the factorization, is because of this bit here. We need to know what P and Q are, and P and Q are these two here, 17 and 19. So the point here is that this number is very hard to know if you don't know 17 and 19 are the factors. You can't get this number easily from 323 without knowing its factorization. So this is a secret that you only have if you know the factorization of your numbers. It's very hard for an attacker to know it. And this number, the fact that if I raise anything to the power of 144, it's going to have a remainder of 1 mod 323, is useful later. And that's why we want to find this number. And it's very useful, it's very nice that this number depends on a secret that only we know. and also then is useful for cryptography. So the next thing we need to do in order to set up a crypto system with RSA is we need to choose some small number that doesn't share any factors with 323. We're going to pick 5. It would be easier to pick 3, but for various reasons, that makes the crypto system even easier to break. You actually don't want this to be too small, but again, we are doing a small example. So in reality, 5 would be way, way, way too small, and I can show you why that is later in this example. So what we've done here is we have set up, we've got some variables that are going to define our cryptography system. These are our public key and our private key. And the private key we derive from using that 144 lambda n. And what we need to do is we need to find, we've got e, which is 5. We need to find a number that we can multiply 5 by to get something that is 1 mod 144. For our case, this is 29. 29 times 5, 145. And the important thing here is that you can't find d easily without knowing lambda n, and you can't have lambda n without knowing the factorization of your big number. So this is also very, very hard to find unless you know that 17 and 19 are the factors. Everyone with me so far? Cool. I will take quiet nods for 10 a.m. on the first day of the conference. So we have now set up a crypto system. We've got our public key and our private key. Our public key is what we need to hand out to anyone who wants to send us a secure message, and that is our big number 323 and our number e, which is 5. And we know 29 is the private key that corresponds to 5, and we can only know that because we know the factorization of our big number. Now, if I want to send a message, let me try and send the message 1443. Well, without loss of generality, we can say that all messages are numbers, essentially, because we can just translate things either through their ASCII numbers or binary or whatever. And I want to send the message 1443, which is NDC in, that's the letters, and that's the alphabet, letter of the alphabet that it is. To encrypt a number, if I wanted to send you this message, and I know that your public key is 323 and 5, what I do is I raise it to that power, e to the 5. I raise it to each of those numbers to the 5th power. That's e. And I get some big numbers out. And then I take the modulus of your big number. So I've used both pieces of information. I've raised my message to that power, and then I've taken the modulus of the other number, 323, your n. And then I can send this to you. And if you receive this message, and you know that you've given someone out your private key, 323 and E and 5, and they've sent you this. How do you recover that initial message? Well, what you do is you sort of do a very similar thing, but in reverse. You raise everything to the power of D and take the modulus. And you're going to have to take my word for it that when you raise 243 to the 29th power, you get 3 mod n. I did do this in Wolfram Alpha. Computationally, this is not actually that expensive to do it with pen and paper. I don't recommend it. And you actually, magically, that original message falls out. And you're only able to do this because you have the private key D, right? And one thing I want to point out here is that if I was an attacker listening on this message, and I know that your public key is E is 5, what I might do is I might go through that message, trying to see if there are any 5th powers that I can determine. Because what happens is if your public key, E, is not very big, maybe when you raise a number to that power, it won't get big enough for the modulo of your big N to kick in. And that's what's happened with 243 here. I could look at that and go, well, I know that's 3 to the 5th power. So probably what the person originally sent is 3. And this is why you want your public key to actually not be the smallest possible thing you can do, even though it makes the process of encrypting messages cheaper because you're raising to a smaller power. It also makes them less secure. So it's a bit of a balancing act there. Right. So somebody has sent me a message. I have now decrypted it. Why does this work? Well, this works because of that definition of lambda n, R144, that we started out with in the beginning, the secret that you can only know if you have the factorization of your big number. When you raise something to that power, you get 1 every single time. That means if you raise something to that power plus 1, you get it back. right? But I've just multiplied both sides of that equation by A. And that's exactly what we do when something is originally raised to the 5th power and then again to the 29th power. Because the definition of D was that if you multiplied it by E, you got 1 more than lambda n, right? We got 29 from it being something we could multiply 5 by to get 145. And anything to the 145 is itself mod 323. Everyone with me? Right? It's cool. That's really, really cool. And that's how RSA works, essentially. Limitations and considerations. It requires large prime numbers. These can be very expensive to find. There are lots of people who've put lots of considerable time, energy, computational power into this. There are things called primality tests, which you can do with large numbers to prove whether or not they're prime, even though if you know they're not, it doesn't mean you know their factors. Lots of things like this. But if you're using a big number for RSA, you want to make sure that it's not known to anyone else, because then they could put in the time and effort to try and find those factors. Or it's not something that's already in use. Sorry, that's not actually true. You want to have big numbers that are difficult to crack. If a big number that is commonly used in RSA has its prime factors discovered and made public, you're going to have to pick a new one and start all over again. This we already talked about. If the public key that you publish is small, you want it to be small enough that encrypting message to you is cheap. You don't want people to have to be raising things to the 29th power if they could be raising them to the 5th. However, if, again, as we talked about, if it's small enough that you raise something to that power and it does not get big enough for that modulo of your big number to kick in, if when I raise something to the 5th power it's not bigger than 323, somebody can just take the 5th root of my number of the public message and recover part of the original message. Right. Without padding, messages can be vulnerable to chosen plaintext attacks. And what padding is it's a bit like putting salt into a password hash. Essentially, if I wanted to know if you had sent the message NDC to me, I'm an attacker and I want to know if this particular phrase is being used in your messages between each other, I can simply encrypt it myself and then look out for those numbers that I get out. Because I have your public key, and I can say, well, if somebody was sending NDC to this person, what would it look like? And that's what a plain text attack is, essentially. And because of the mathematical structures of what makes RSA tick, there's sort of very sophisticated attacks that you can do where you take sort of chunks of plain text and it basically, not enough time to go into it, and I don't understand it all fully, but there are lots of different plain text attacks you can do with RSA. And one of the ways we get around this is with padding. So fun history anecdote here. This is before RSA, right? But this is a message that was sent to Admiral Bull Halsey. And this is just plain text. In pink, we have padding that is sent to just, it's sort of like obfuscation, essentially. And then we have delimiters, so GG and then RR, sort of like the open and close brackets of here's the actual main text that I want you to read. And then at the end again, we have more text, more padding text, right? And Admiral Bull Halsey was an American naval admiral, and the operator who decrypted this message misinterpreted the padding, right? So this might have been encrypted with, a Caesar cipher of some kind. He misinterpreted the padding. He missed that last delimiter, that RR. And so instead of saying, where is the Task Force 34, he passed the message on along as, where is Task Force 34? The world wonders. And Admiral Bull Halsey interpreted this as a sort of passive-aggressive, where is Task Force 34? The world is wondering, instead of it being just, nonsense text that was put in to sort of as obfuscation. And he locked himself in his room and had a tantrum. Not particularly, it's not asymmetric encryption, but I think that's quite a funny example of padding going wrong. But padding is a technique we can use in order to reduce the effectiveness or availability of plain text attacks, essentially. For example, if I know that every message that you're going to send to me, you're not actually going to send to me NDC, you're going to send like N1, D3, C5 or something, and you're adding odd numbers in between each one. I know to discount each second character. That would be a form of padding. But an attacker doesn't know that. However, in order to get to that situation, you need to have some shared understanding of what the padding is going to look like. So we're back to the symmetric encryption problem. Okay, we are now on to the group theory part of the talk. Who here has studied group theory in any formal capacity? Okay. The rest of you are, you're one of today's lucky 10,000. So we've been talking about modulus arithmetic, and modulus arithmetic is one of the easiest ways to understand group theory. What's going on under the hood when we do this is essentially we've said, okay, let's say we're working in modulus 11. We're considering any number that is differ by a multiple of 11 to be the same thing. We've essentially said, okay, there's not infinity numbers. There's only 11 numbers. There's 0 up to 10, right? And what we do, the way that we operate in this, is that when you get back to the top and you want to do 12, you just loop back around and you get 1. And this is quite intuitive. We all understand this. This is how clocks work. I've got a bit of a misshapen clock here because it's only 11 elements instead of 12, but this has really nice mathematical properties if you do it with prime numbers. So this is a group, and a group is a set of objects that has satisfies 4 conditions. 1, there's got to be some integer, there's got to be some element, sorry, not integer, there's got to be some element that does nothing to all the other ones. And if we're looking at addition, that's 0. When you add 0 to something, nothing changes. When you add something to 0, nothing changes, right? So we are working with these numbers and the addition operation. A group is a set of stuff and a thing that you can do to combine 2 of those things. Anytime that you can, you've got to be able to combine 2 elements to get back to 0. For any element in this group, there's got to be something you can add to it that takes it back to the identity element. So in this case, it would be, for example, 4 and 7. When you add 4 to 7, you get back to 11, which is the same thing as 0, right? And in our case, what you end up with is every element is opposite its inverse on the ring. When you combine 3 elements, this is called associativity. It doesn't matter which order you do the operations. And luckily, we get this for free with addition, but it's not true of something like subtraction, for example. It matters which order you do those operations. And this is why we end up with things like BIDMAS, BODMAS, PEMDAS, things like that, those rules about which order do you do things in. Because this stuff can get messy when you're dealing with more than one operation. Fortunately, addition and multiplication, this is just true. When you add 3 things together or you multiply 3 things together, it doesn't matter if you do one of those operations first or the other, you get the same answer. And every group has to satisfy that as well. And the last thing is, if I've got 2 elements and I add them together, what I get out at the other end is also a member of that group. So these are the 4 things that you need in order for a set of objects and an operation to be a group. And once you know that something is a group, you can do all sorts of nice theory with it. And you can start proving all sorts of things. So we've been talking about addition for this group, which is the group operation here. But we also have, in regular maths, we have a shorthand for if you add something to itself repeatedly. We call that multiplication, right? Let's say we add 4 to itself 13 times. We could write 4 plus 4 plus 4 plus 4, or we could write 4 times 13, and then we get the number 52, right? And what I want to make clear here is that the 4 we're talking about is the 4 that lives within this group. But we've added it to itself 13 times, and that's a thing you can just do under this group law. But when we start using that shorthand of multiplication, we're not talking, this 13 isn't a member of the group. What we're talking about is having added 4 to itself 13 times. This is shorthand, this is just notation. We're not doing multiplication within our group, we're doing lots and lots of addition. Everyone with me? And what we get out is a number that's also not part of the group, but we can do modulo 11 to it and get a number back. And if you add 4 to itself 13 times, you go around the ring a bunch of times, you do end up at 8. So what we can do here is we can use the shorthand of multiplication that we are known and familiar with to sort of briefly operate outside the group and then come back into it, as it were. So we have the idea of adding an element to a group, combining it with itself multiple times and using the multiplication shorthand to represent that, right? But it doesn't mean that 13 is an element of the group. For example, what if we changed all of these elements to not be numbers anymore, but simply symbols that have the same relationship to each other as the numbers did? You know, star times 13 is club symbol. It makes it more obvious that what we're doing is we're not talking about regular maths here, we're using this shorthand of notation to talk about combining things with each other multiple times, right? Another example of a group that you might be familiar with is all the ways that you can rotate a cube. right? If I do one rotation, like, oh, I'm going to move the cube like this, and then I move the cube like that, what you get out is a thing that you could have gone like this to do. That's pretty abstract, but you know, if you want to know more about group theory and things, this is like a really cool example to start with because it sort of makes it clear. It's another example that is not based on numbers, because the ones that are based on numbers can sometimes lead you astray with how similar they look to the maths that you're familiar with. Right. So what we have is we have a group definition. We've got a bunch of things, and we've got a thing, and we've got an operation we can use to combine two of them, get something else that's also part of the group, and so on and so forth, with all of these different laws. And obviously modulo arithmetic satisfies this. And you can explain how RSA works in terms of some of the group theory that's involved. We are now going to talk about elliptic curve cryptography, which also relies on groups. And so that's where a lot of what I've just been talking about is going to become, you'll see why I've been belaboring some points. So elliptic curve cryptography is what has essentially in large part superseded RSA as a public key cryptography system. For a few reasons. It is faster to do, you can have smaller key sizes, and sort of various nice cryptographic properties, essentially. And how it works is it also uses groups. But the group isn't numbers like RSA is. It's something a bit more abstract. So an elliptic curve is a function of the form y squared is x cubed plus some multiple of x plus some constant. And depending on how you change those the a and the b there, you get lots of sort of different shapes, and some of them have points, and some of them are disconnected from each other, and things like this. The ones that we're interested in here are sort of this shape, where they've got this sort of almost horseshoe thing, and then on both sides, what they do is they continue on up, and they never quite become vertical, but they become asymptotic to the vertical. And what we do is we try and solve this equation, but specifically only for modulo arithmetic. So all of the solutions that I care about for this equation are the ones that live in, let's say, the numbers between 0 and 10. And we're always working modulo 11. So we're not working over the field of like real numbers. We don't have like fractions, we don't have square roots, we don't have any of that. We just have whole numbers, and the ways that they relate to each other, we're always working in modulo 11. And what that's called Z, which is the integers, and then with that little p underneath means we're working mod p. And this forms what's called in maths a field. For our purposes, we only really need to care that it's also a group. And the group combination law, so we're taking these points and we're saying, okay, we've got this group, we've got this set of objects, right? These blobs that correspond to solutions. And we want to be able to combine them. We want to be able to give them a combination operation that satisfies all those group laws, so we can start doing nice group theory with them. And the group law that we come up with is, okay, if I combine any 3 points, if I draw a line between, let's say, these 2 points, it will intersect the curve again, unless it's a tangent to the curve. It will intersect the curve again. And this gives me 3 points, right? And those 3 points sum to 0, the identity element, which is, we say it's the element at infinity, which is a bit of mathematical cheating that allows us to have an identity element. Essentially, it's saying, okay, infinity and infinity, if y and x are both infinity, it's infinity equals infinity, so that's the solution, right? And technically, our curve kind of gets there, right? Because it stretches off into infinity. So it's a bit of a cheat, because infinity is not between 0 and 11. But we say that this is the identity element. And the way that we add things, essentially, is by this group law. So this and this is minus this element, because you can, so if, hang on, do I have a better illustration of this? Yeah, here we go. I've got 3 points on my curve, and I said, okay, these 3 points sum to 0, essentially, the identity element, which means that this point here, C, is the identity minus a plus b. And minus a plus b is the inverse of a plus b, because everything has an inverse in a group. I'm getting confused looks. Which bit where am I losing you? Yeah? No, it is not, and that's why I'm trying to use, this is not actually a 0 in the thing, it's the capital O. Yeah, it's the identity element, yes. 0, 0 is not going to be a solution to the curve unless b is 0 in that equation, yes. Yeah, thank you for clarifying that. 0, 0 is not interesting to us. Yeah, I'm talking about the identity, the infinity point. So I'll call it the infinity point now. So we've got this rule, a plus b plus c is the infinity point. And we can move stuff around on this equation because we have the idea of inverses of things, which we can use the shorthand of subtraction to denote. So c is the identity element plus the inverse of a plus b. So what we do is we have now a group law that says if I have a plus b, what I have then is, what I have is that c is minus a plus b. So a plus b is minus c. We have a group addition law now to take 2 points and we combine them and we get another point on the curve. You don't have to understand this fully. My main point is, and for what it's worth, the inverse of c is the mirror point below the x-axis. What we've done is we've defined a law, that a way to combine two elements and get a third that happens to obey all of those group properties we talked about. We've defined a group over these points. Now, there are ways that you can confuse yourself, essentially, or not confuse. What happens if you do the same? You draw two lines. You draw a line between 2 points, but that line is vertical, right? It never intersects the curve again. So how can we know what C is? Well, we just say that when we add those two things together, what we're getting is the infinity point. And that means that A and B are inverses of each other. We say that this line intersects the curve again at infinity, our infinity point. So we can just cancel those two things out and say A plus B. Or the entire definition of the infinity point is that when you add it to something, it does nothing, right? So actually A plus B is the infinity point, and therefore A is minus B. So this is how we get our inverses in this group law. Right, okay, enough of the more abstract stuff. Here is an actual elliptic curve, which I wrote by hand. If you want to come and see my messy handwritten notes about this, you can. So I chose a formula, I chose a graph, and I solved it for all of the solution points in modulo 11, right? This is an actual elliptic curve, right? And one of the nice things about this curve in particular is that it has 10 solutions in it, and then you get the point at infinity. So you're working modulo 11, and you actually have 11 solutions. You might get a smaller number of solutions, but when you're working in a prime field, modulo something, you actually want as many solutions. The most you can have is 11 for 11 things, including the point at infinity. And this is preferred for elliptic curves. So this is, if you're working modulo 11, which is don't do this in production, this is actually a very nice example of that, so I was quite proud of myself. And when you do elliptic curve cryptography, you have a public key that you need to publish, right? And just like with RSA, this is formed up of a bunch of parameters to do with the system that you've chosen. So like we chose 323, 17 times 19, I have chosen this elliptic curve. That's the same, it's a similar thing. I choose a big number or I choose a curve and a prime field to work over. What we publish is a bunch of information about our elliptic curve. So the first thing is, it's called, by convention, this is the notation you use. T is the thing that you publish. So the first thing you need to know is the integer that you're working modulo. And in our case, this is 11, right? The next thing is A and B, which define our curve. After that, we have a graph point, a point on our curve, one of those blobs. We choose a special one of those blobs and we publish it as our public curve point. The next thing we have is these next two are pretty abstract and you don't need to worry about them too much. The n is how many times, when I add my special curve point to itself, how many times does it take to get back to the identity? You know? And so we hope that is, if you think about the clock, how many times does it take to add 1 to itself before you get back to 11? Well, 11. How many times does it take? 3. It's actually also 11. But if we were working with a regular clock face, you would only have to add 4 to itself 3 times to get back to 12, if we're talking about a regular 12-hour clock face. So the order of 4 in that system would be 3. But when we're working with prime numbers, that number is always that prime number. And then the last thing is very abstract. You don't need to know it, but the main thing is that you like it to be 1. Wait, hang on. Yeah, you like it to be 1. And you don't need to know much about that. Is what I was talking about when I was saying you want there to be as many points that are solutions within your field as possible. It's nice that I had 11 solutions. That's what that means. For all the group theory nerds, we're not talking actually about G, we're talking about the orbit of G, but yeah. Yes. All right, we've come back to our curve, and so I'm going to illustrate what each of those parameters are. So, P is 11 because we're working in module 11. A and B are 1 and 5. G is I have chosen a special point on the curve. I like this one the best; it's my favorite, and that we publish as our public curve point. This is equivalent to E. We just pick a number and we publish it. And in RSA, you needed your E to be co-prime to your big number. Here, we need this to be some point on the curve that's not the identity element, right? And then N and H are 11 and 1. And those will always multiply to the field that you're working in, right? Which means that they have to be 11 and 1 if it means that they have to be if you're working in a prime. You're not always for elliptic curve cryptography, but for our purposes, we can assume they are. Right. In previous versions of this talk, I did a worked example here of the elliptic curve digital signing algorithm. I learned that it doesn't work as a live thing, because if you think that you've been zoning out so far, trust me, you would be zoning out a lot more during this. If you do want to see it and go through it, come to me afterwards. It's at the end of the slides. The main thing that I want to get across about an elliptic curve, right, is we've got our special little point here. And when you add it to itself, you get another point on the curve, because we can do our group multiplication law. And when you add a point to itself, you know that it was like, oh, we've got to draw a line between 2 points. What you do to add a point to itself is you draw the tangent line to the curve at that point. There's also algebraic ways of doing it, like I can work directly with the fact that it's 0, 4, and you go to the Wikipedia page to know if you want to know about the algebra that I actually did to get all of these. But in the abstract terms, it's you draw the tangent point to the curve, and where does that intersect the curve again? So when you add 0, 4 to itself, our special point, when you've got 2 lots of it, we get this point. And if we do it 3 times, we get this one. And so on and so forth. And what you get is you end up looping through all of the other points. So what we've got here is our numbering. It's just a bit mangled, right? We've got the same thing. We've got 1, 2, 3, 4, and eventually we'll cycle around all of them. We'll get back to the identity, which is 0, which is equivalent to 0. So we've got exactly the same structure that we did with that modulo 11 numbering, right? But we've just defined this to be 1, and we've got a different way of adding it to itself. But the way that we combine it means that we can basically use a lot of the same notation. It behaves a lot of the same ways. So what you end up with is this elliptic curve having this structure. If we say, okay, I'm going to choose this to be my special point, we can define all of the other points in terms of that. And when we add it to itself 11 times, we get to the identity point, the infinity point. And we've got inverses, because do you remember how our inverses were the mirror below the x-axis? 4 and 7 are mirrors below the x-axis. So even like with the numbering, you add 4 and 7 together, 4 lots of my special point and 7 lots of my special point, you get back to the infinity. So it really has that exact same structure, essentially. We've got back to our numbering. And the main point that I want to make here is that we've got this sort of really abstract mathematical object, and using this one instead of numbers gives us certain properties, like it has a smaller key size per security and smaller payload size. So you need to have smaller secrets, and you can send messages that have that are smaller to send. And it's also very fast to do the computations for curve addition on an elliptic curve. It's faster than it is to do raising things to the power, for example. But they're very, very similar mathematically under the surface. There's how RSA is based on it being very hard to factor big numbers into their prime factors. Elliptic curves using them for cryptography is based on the fact that if I have 2 points on an elliptic curve, it's very hard for somebody who doesn't already have all of the curve, like doesn't already know everything about the curve, to figure out how many times you had to multiply one to get to the other. It's very hard to, it's easy to go, okay, I've got a special point, and I'm going to multiply it by 7 and send you that point. It's very hard for somebody, given those 2 points, to reverse engineer that operation, essentially. And that's called the elliptic curve subgroup, I think. It's later in the slides. So this is great, right? We've got this shiny new, better thing. Most people are using elliptic curves, smaller payloads, faster computation. This is great. It has superseded RSA in almost every scenario. Great, right? Not so great, because we keep inventing new things, and one of the things we invented is quantum computing. And quantum computing breaks everything that I've just showed you. Here is why. So we're talking about hard maths problems. The integer factorization problem is what powers RSA. It's very hard to find factors of big prime numbers. Then we have the discrete logarithm problem. That's the words I was looking for earlier, which is essentially it's abstract to explain, but it's essentially, and the similar one, which is the elliptic curve specific one, maybe easier to explain because I've just been talking about them. If G generates a subgroup, or the entire group, of an elliptic curve, so our special point, when we multiplied it by lots of stuff, it gave us the whole group back, right? We had that. So G generates some group, right? And by generating, it means, can you add it to it? What do you get when you add it to itself lots of times? And I have some other point that is generated by, let's say, multiplying my special point by 7. It's really hard to find, it's really hard to get 7 back out of that, essentially. It's something which is really easy to do in one way, multiplying 2 numbers to get a bigger number, and really difficult to do the other way, factorizing that number back again. So analogous problems, right? And these are the problems that power RSA and elliptic curve cryptography. Now, in 1994, year I was born, a guy called Shaw wrote some algorithms, or published some algorithms, designed for quantum computers to run. There weren't quantum computers then, hadn't built them yet, but he knew they were going to exist, and he had some idea of how they would work, and he wrote some algorithms. And the one we care about today is Shaw's order-finding algorithm. And what it does is it says, okay, this is a thing that's hard to do on a classical computer, but on a quantum computer, you can do this in reasonable time. For any given number, n, any number at all, we can find, and any number that we have in between 1 and that number, we can find the smallest number such that raising our second number to that power gives us 1 mod n. Right. Basically, if I have a and n, I can find the smallest r to make this true. This is really hard to do classically, but quantum computers can simply just do it, right? So if we go back to our example of RSA, n equals 323, we'll choose an a that's in between them. So we have our 2 things, a and n. Shaw's algorithm gives us, for free, that if I raise 11 to the 48, I get 1 mod 323. I didn't use a quantum computer for this. I typed it into Wolfram Alpha for like 15 minutes. But this is true. And Shaw's algorithm just gives us this for free. And in a production scenario, I would not be able to just type this into Wolfram Alpha. I would need a quantum computer to do this. But because this is a small example, it works. And the way that we can use this to factor 323, we can solve the integer factorization problem, works like this. So I know that 11 to the 48 is 1 mod 323. And we have the difference of 2 squares rule. So 11 to the 48 minus 1 must divide by 323. And we can do the difference of 2 squares. And we can say, OK, so 11 to the 24 minus 1, or 11 to the 24 plus 1, but one or both of those must divide 323, right? We know 323 doesn't divide into 11 to the 24 minus 1, because we know that 48 is the smallest r for which this is true. And if 11 to the 24 minus 1 was divisible by 323, 24 would be smaller, a smaller number that made this thing true, which it's not. So we know that some of the factors of 323 must also divide this number here. And if we're unlucky, then all of them do, and this simply divides by 323. And if that's true, then we pick a different a and start again. But it's better than 50% odds that this is true. That only some of the factors and not all of the factors divide this number. So at least one of the factors of 323 must also divide 11 to the 24 plus 1. And we can pick A to make this true with a few attempts will basically pretty much guarantee that we can find this scenario. We can calculate the greatest common divisor, and this is cheap to do computationally on a classical computer. And we find that there is a greatest common divisor of this, and it's not 323, not both of the factors, only one of the factors. So we found one of the factors of 323 by using that Shor's algorithm giving us this power that we can raise a number to and get 11323. We find that 17 divides 323, also very, very easy to check. And therefore, we have factorized 323 using Shor's algorithm. And I've cheated a little bit here because of this bit, in the sense that I got lucky. I didn't have to do this multiple times. But it is possible. There's two ways that this can not work on the first attempt. One is that 323 itself divides this, and you've learned nothing. The other is that this number, 48, this bit only works because that's even, right? It's only a square because 48 is even. I could have found that actually I picked a different A and I got 23 out. And that would have been really annoying, and I would have had to start again and pick a different A. But we have like 300 odd possible values of A that we can play with. And all of this is computationally cheap if we're using quantum computer. So that is how Shor's algorithm, Shor's order-finding algorithm, breaks the integer factorization problem and therefore breaks RSA, right? So yeah, integer factorization problem, boom, gone. RSA, can't use it. Quantum computer's going to break it. Quantum computers have now been used to do the integer, like factorize. I think they factorized 15 into 3 and 5, which is very cute. But they used Shor's algorithm to do it. As it happens, Shor wrote some other algorithms that also kill off the discrete logarithm problem for both regular numbers and for elliptic curves. So ECDSA, elliptic curve cryptography, boom, gone. Can't use it anymore. So what do we do next? And the answer is post-quantum cryptography. So everything is powered by hard problems. It so happens that Shor's algorithms kill the hard problems we have been using. It doesn't do that for every problem that there is. So we need to find different hard maths problems to power new quantum encryption schemes. There is one called the isogeny finding problem. And I'm just going to read this out really quick. This was first proposed in 1997, so only 3 years after Shor published his algorithms. It described a non-interactive key exchange protocol where the space of public keys equals a set of FQ isomorphism classes of ordinary elliptic curves over FQ whose endomorphism ring is a given order O in an imaginary quadratic field and whose trace of Frobenius has a prescribed value. So take that back to your workplaces and say you got value out of this conference. Basically, it's a hard maths problem that people use to try and make new crypto systems in the same way that we've used hard maths problems to do RSA and elliptic curve cryptography. It gave rise to a couple of crypto systems called Psych and Seed, which are now considered insecure. Also one called Seaside, commutative supersingular isogeny Diffie-Hellman. This work on this crypto system was started while close to a well-known body of water, and that's why they call it Seaside. This paper actually, so there's oh, this isn't the paper. There was one that was like she sieves by the seaside or something, which is very funny if you're a cryptographer. They love their puns. But this was also shown to be not as secure as it should have been for a given key size. So Seaside is also considered insecure now. And I don't know what work is being done, if any, on using this hard maths problem to create crypto systems. However, there are others. The learning with errors problem, which is essentially introducing noise into the process of cryptography. Now, I understand some maths, like I have an undergrad in it. This is witchcraft, this stuff. It's absolutely incredible. The learning with errors problem is essentially introducing noise into your encodings and doing some kind of incredible probability stuff at the other end to recover the original message. And this is what has given rise to the next generation of NIST has said that these are the NIST's candidates for post-quantum resilient cryptography systems, and you can use these today. So Crystal's Kyber and Crystal's dilithium, so Star Wars names. And Kyber does key encapsulation, which is what I was talking about at the beginning, where asymmetric encryption is used to set up a shared secret so we can do symmetric cryptography, which is very efficient and very hard to break. Kyber is what lets us do that in a way that's not vulnerable to quantum computing attacks. And dilithium is what lets us do digital signatures in the same way the elliptic curve digital signing algorithm does today. And so what people are doing at the moment is they're combining traditional elliptic curve cryptography with these new quantum resilient ones that are based on the learning with errors problem. And this means if one is broken, the other one is still there, which is pretty reasonable, honestly. One of the difficulties of getting this dilithium algorithm, this is the key, this is a signature algorithm. One thing we really like in security, we like having hardware tokens for all the reasons, they're very hard, they're very resistant to phishing. I have a whole talk about why they're really cool. But getting the algorithm small enough to run on these hardware tokens, and I think they actually ended up using Rust to get the algorithm small enough to actually be able to run on the hardware tokens. But quantum resilient hardware tokens, I don't think are being manufactured yet, and the scheme has not been fully adopted by the FIDO Alliance. Hopefully sometime soon we'll see that. Digital signatures, we do have quantum resistant digital signatures as long as the learning with errors problem isn't solved by some other kind of quantum computing that comes out. Similarly with key encapsulation, in Chrome you can enable X25519 Kyber 768, which is a combination of traditional X25519 certificates or key encapsulation stuff, and also some stuff done by Kyber. So you do 32 bits of each, and then if one is broken, the other is still not compromised, although you now only have 32 bits of security. So it's a nice way of like hedging the bets. And Cloudflare does this as well. If you use Cloudflare, Cloudflare will talk to Origin servers in quantum resilient crypto systems, cryptography, if you have that enabled, which is really cool. Cool place to go and learn more about what's at the cutting edge here is Open Quantum Safe, which is a sort of open collective of people who are working on this stuff. I was very tempted to get back into writing C so that I could go and like contribute to some of the libraries. And so where I hope this is all going to go next is I would hope to see more diverse algorithms. So at the moment, we've got Kyber and dilithium that are based on the learning with errors problem. That's one problem. If we find that this problem is solvable even by classical computers, probably not, but by some quantum computing algorithm that hasn't yet been written, these go bye-bye just like ECDSA and RSA did, and that would be bad. This is unlikely because they have had so much attention. Like if you manage to break Kyber and dilithium today, that's instant like fame in the cryptography community. So there's lots of people who are trying to do this. It took the isogeny finding ones, Psych and Seed and Seaside, it took them a little bit longer to be broken. Like they went through a couple rounds of reviews before they were eventually broken. And they were broken by classical computing, not even quantum computing. But they didn't get as much hype. They were much niche use cases due to some of their computational properties. So I think it's very unlikely that Kyber and dilithium will be broken in the same way that RSA and ECDSA are. Hi. Sorry? Oh, sorry, yes. So Kyber is the key encapsulation mechanism, and that is used during a TLS handshake. So the key encapsulation here means it's encapsulating a key that is supposed to be shared between two people so that you can do symmetric cryptography, which is what the bulk of web traffic is encrypted with. So yeah, the thing to look up for Kyber is key encapsulation mechanism, and that's what that does. And then dilithium is for generating signatures in much the same way as elliptic curve digital signing algorithm does. Does that answer your question? Cool. Please come and talk to me afterwards. Yes. So I would like to see more algorithms based on other math problems, just to give us a little bit more security, a little bit more diversity of tactics, as it were. Plus, I think it's cool. There are people doing this. There are other hard math problems where people are trying to develop crypto systems, but a lot of the attention right now is probably going to hardening Kyber and dilithium, making extra sure that those are reliable, because we're trying to roll them out to more and more web infrastructure. I'd love to see quantum resilient hardware tokens. I think hardware tokens are the bee's knees. I think they're really, really cool. And I'd like to see the cool, shiny new algorithms running on them. I think we should see this in the next few years. It just needs a bit more sort of standardization, for various standards bodies to agree on things and for things to sort of get a bit more formalized and settled. And I would like to see wider accessibility and rollout of the availability of these new cryptography systems. So one of the issues with this, for example, is that during the TLS handshake, so that there's a thing called client hello that gets sent from the client to the server as part of the setup. And with elliptic curve cryptography, that usually fits within one packet, that encrypted bit. If you're using this hybrid algorithm where you're using part elliptic curve, part new Kyber, that actually doesn't. So you have to split up the client hello between two different packets. And some softwares, that should be fine. Per the TLS spec, you are allowed to do that. But a lot of software has made the assumption that it will never happen because it hasn't been happening, right? And that's how things go. So we have this called, I forget what the exact terminology is, but it's something like protocol ossification or something, where this is how things kind of have been, even though they don't have to be, and it becomes a de facto standard, even though it was never supposed to be. So that's things like that, really annoying, obscure things like that are getting in the way of us just being able to roll this all out immediately. And there's various ways that we can approach that particular problem and similar problems that arise. So that work is just ongoing. I'm hoping to see more of it happen and for us to be able to just be using these quantum resilient algorithms in our everyday. Something I haven't touched on at all is why we should even care, right? People don't have quantum computers today to be looking at our traffic and looking at your bank details or whatever. And I'm not a state actor, so I'm not that worried. But the thing is that it's very cheap to store data. And if I'm sending stuff that's only encrypted with elliptic curve cryptography today, somebody could be storing that. And then when they do have a quantum computer, because in the 50 years quantum computers will be cheap and we'll all have them in our phones or whatever, then they could decrypt it. And depending on who I am, what I'm saying today might still be relevant 50 years from now. And again, this is more something that you need to worry about if you are a state actor, if you're a government, or so on. But it is true, the sort of harvest now, decrypt later sort of idea. And that's why people should be using quantum resilient algorithms today. I would like to see more of them, and I would like to see them become more accessible, easy, one click and we can just do it. But yeah, that wraps me up essentially. What we've learned is how we got to where we are today. We've learned about symmetric cryptography, we've learned about RSA and ECDSA, lots of abstract maths. Thank you very much for staying with me through it. Lots of colorful blobs and curves. We've talked about quantum encryption, or quantum mechanics, Shor's algorithm. You've seen directly how Shor's order-finding algorithm can break RSA. And we've talked about what's next. Thank you very much for your time and attention. I hope you've enjoyed it, and I hope you enjoy the rest of this conference. It's going to be really, really good. Thank you.